Electromagnetic energy is the energy that's carried by electrons moving through a series of wires or electromagnetic waves moving through space. And so like all of our forms of energy, we're going to measure it in joules, and electromagnetic power is going to be measured in watts. In the diagram in front of us, we see a voltage source, so a battery. So that's providing electrical pressure, is a way that we can consider it, that drives the flow of electrons around the circuit. So we've got electrons that leave the positive terminal, flow into and across some load, where there's a commensurate voltage drop to what is supplied by the battery, and then those electrons complete the circuit by re-entering the battery through the negative side. And of course we know that is backwards from reality. In fact, the negatively charged electrons flow out from the negative terminal and flow back in through the positive terminal, but our misconceptions date back for hundreds of years, and so we've stuck with this conventional diagram. It's important that we understand the concepts of work and power in an electrical context, just like we do in a mechanical one. So in a mechanical system, we know that work is defined as force times distance, or power is the rate at which that work is being done. In an electrical system, if we work backwards a little bit, so first of all, the concept of force in an electrical system is going to be defined as the charge of Q coulombs in a voltage gradient times the voltage drop divided by the distance of that voltage drop. So we've got however much charge we have times the amount of the voltage drop divided by the distance of that voltage drop. And so then if we take work, remember work is force times distance. So we're going to take this force as defined in an electrical context and then multiply that by a distance. Well, we can hopefully see where that's headed, where we're going to be able to cancel out our distances here, and so we're left with just a charge times a voltage. Now, if we go farther, we can find power is going to be the charge times the voltage, so that's work, divided by time. So that's what we see here. But this Q over T, this charge divided by T, what that really is current. And so now what we can do is we can substitute that Q over T for current, and so then we get what's known as the electrical power law. And so the power in an electrical circuit is defined as being the current times the voltage drop. And this power law, coupled with Ohm's law, where voltage equals current times resistance, allows for the analysis of some simple circuits. Now for our purposes, we're just going to focus on the power law since we're dealing in a chapter focused on work and power, energy, but in our electrical engineering unit, we'll spend a little bit more time studying more advanced circuits involving multiple loops that will build off of your work from physics. So in a simple example here, we have a battery that sustains a voltage drop of 3 volts across a small light bulb. It produces a small 0.10 ampere current through the light bulb. So we want to know what's the power required by this light bulb. So we have our power equals current times voltage, which we derived in the previous slide. So we're trying to solve for the power, given a current of 0.10 amps times a voltage of 3.0 volts. And so just through simple multiplication, we end up with a power of 0.30. Again, remember the units for power are watts.